you will be able to access your designated lab. So let's carry on where we left off last week. So essentially, last lecture was about the neutral axis and the centroid of composite objects. So basically, the quick equation was the neutral axis about the x, and we said the NAX. Let me just grab my marker here quickly. What is it? Here, the NAX will give me, or rather, will be reported by the y bar, and the NAY will be reported by my x bar. And those are the equations. We practiced those last week quite very well. So now let's move on to the other topic that we want to talk about today, which is the moment of inertia. And this slide is basically another example. And in here, it's what we are saying. It's important to be able to know the neutral axis or the centroid of the common shapes, and those are rectangles, squares, and triangles. Now, the moment of inertia. What is a moment of inertia? From a definition perspective, it is a mathematical property of the area that describes the second moment of area about an axis. So there is a lot of terminology happen in this definition, but let's break it down. So now what we said, let me grab my marker, we said it's a mathematical property that describes the second moment of area about an axis. So what's the key here? The second moment of an area. To help you understand how this definition translates into this equation, just to help you understand how this definition, verbal definition, translate into this equation properly, let me clear this room, board, and do it one more time. If I were to say, what is the moment of a force? If I were to ask you, what is a moment of a force? Basically, you would say, okay, I have a force in here, and let's say this is a support in here, and the force is applied in here. We all agree there will be an internal moment in here. And we would ask, how do we quantify this moment? We said simply it's going to be the distance, d, multiplied by my force. So that is known as the moment of a force. Now, what we are saying here, it's what we need to get at is a moment of area about the neutral axis. So now if I've got an object, and I know, let's say the point of interest, which is the neutral axis, is this point in here, this line in here. So the moment of an area would be the center of that area, which is that point in here, and the moment of an area would be the distance from here to here. This is distance d. And we saw that clearly with the centroid equation. So and that's what we say, that's what we did in the centroid equation. But let's carry on. So what we are saying, moment of an area would be simply, let me grab my marker, would be that distance d multiplied by an area. This is called moment of area. Now, what the moment of inertia, it takes the second moment of an area. Second moment of an area, meaning that distance has to be squared. The third moment of an area, this distance will be cubed, and so on and so forth. So now, let me just clear that up some more. So the moment of inertia is a mathematical property of area that describes the second moment of an area. So now that's what we look at this equation. It is the summation of all the smaller segments, and all what we need to do to take the distance, right? We need to take the distance from an axis in here, and in our case, it has to be the neutral axis. And all what we need to do, we need to get the second moment of an area, and to get that in an equation format, it will be the distance from the neutral axis to the center of that segment area, and we multiply by that area. Of course, that distance has to be squared, hence the y squared. So this is basically to get your head wrapped around how does the definition, the text, translate into this mathematical operation. So at least when you look at it, when you read a definition, it's in line, so it helps you understand it a little bit. But now let's move on to say, what does this tell us? What does it describe? And it describes the object resistance to bending and deflection due to angular rotation. So when an object is subjected to bending, a rotation occurs about some axis in that shape. This axis is referred to as the neutral axis. That's why the first lecture was so important for us to learn how to calculate or how to find the neutral axis of a given object, because we will be using this point, this neutral axis, to add and build on other information, such as the moment of inertia, and later on with the section modulus, which we will be introducing to you as well. So now if you were to imagine this is the shape in here, a beam, and the cross-section of that shape is a trapezoidal. So clearly the neutral axis will not be centered on the depth of that member. It will be shifted a little bit down. Now if I were to take that object and apply some load on it, and this object would want to flex, what you will note, the vertical lines before the object was loaded formed a 90-degree with the neutral axis. Now, once it's loaded, you will note that the vertical line that was previously drawn will also continue to form a 90-degree with the neutral axis. And what this tells us in this relationship is the neutral axis is the point that will receive no tension nor compression. Because if you look at the upper half, clearly you would say the object is being compressed, or the fiber at the utmost top of that object is being compressed. And if you look at all the way at the bottom, you will see the fiber at the utmost bottom face of this object is being elongated in tension. But at the neutral axis, you will have zero flexure stresses. So far, so good. Let me have a look at the chat. All right. Chelsea, you asked me a very good question. And this is a very, very good question. Note something, that when we are taking the centroid, we would use the first moment of an area. Now, when we are using another geometric property we will introduce to you, which is called Q. And it's basically the first moment of an area, and we will use that when we design for shear. That uses a first moment of area. The second moment of an area is used for the moment of inertia. Now, if there is to be third or fourth or fifth, those are not yet used in our structural analysis. They may have different applications, but definitely not in our regular beam flexural analysis. So for structural design, we only go up to the second moment of an area. Oh, I'm reading the chat and I see what you guys are working on. Basically, the moment, haha, very funny. So now let's get back to our moment. So the moment of inertia is given by this equation, and this equation in here, if you look at it, it uses the sigma, which is basically the summation of all of the individual parts. Let me just close the chat a little bit. Okay, there you go. So I would be the moment of inertia about the x-axis. Y would be the distance from the neutral axis, and give me one more. And delta A would be the increment area being considered. That's what A is. So now if I'm looking at this rectangular shape, right, and I would like to take the moment of inertia about this object, and let's say I am going to divide this object into two segments. So I have dividing it into two segments. So I have a rectangle, a square at the top, another square at the bottom, and I would like to calculate what is my moment of inertia based on this two square division. So simply I will take this equation, I will say the summation of all of the segments. So I've got two segments, so therefore I've got two terms. Term representing the top segment, another term at the bottom representing the bottom segment. So now, what is the distance from my neutral axis to the center of the first segment? What is that distance equal to? It's going to be 2 inches. Oh, I'll tell you why. So that's a very good question. Now, if you kept it as 1, the first iteration on the equation, it would be 0. Because if I kept it just at 1, I will be asking you what is the distance between the neutral axis and the center of this rectangle. That distance y would be 0. Right? So the moment of inertia would be 0. That's the first reading based on this division. You don't divide it into anything. Now, what I'm saying now, let's divide it into 2 and see where this leads us. Is it going to give us 0 or is it going to give us another value? And what is that value? So basically, we've got the area of the segment number 1, which is going to be 4 by 4. This is my area. And the distance from the neutral axis to the center of this segment, it's going to be 2 inches. So I've got 2 inches squared. The same thing will happen at the bottom. I've got the area of the bottom face, which is going to be 4 by 4. This is my area. And the distance from the neutral axis to the center of this segment is going to be 2. Note, I'm going down on my neutral axis, so it would be minus 2. No matter, it's minus 2 squared. That's fine. So what is the answer when you calculate all of that? It's going to be 128, and the unit is going to be inch cubed. Of course, this is a typo in here. There is no inches in here. There is no squared in here. So basically, I've got inch square multiplied by 1 inch multiplied by 1 inch added to another inch square multiplied by 1 inch, 1 inch. So the unit is going to be inch to the power of 4. You see that? So now, back to a sketchy comment. If I were to use only one single rectangular piece, quickly, my moment of inertia is 0. So I'm going to divide it into 2 pieces and see what is the moment of inertia on that. Divided into two pieces, I've got the moment of inertia of 128. Fine. Now, what will happen if we decided to divide this into 4 pieces? What happened? What will happen if we decided to divide this into 4 pieces? The same equation now, instead of having only 2 segments, I will be getting 4 segments. I've got segment number 1, 2, 3, and 4. This is my neutral axis. And the area is going to be 2 by 4, the area of each segment. So that's 4 inches by 2 inches. This is the area of every single segment. All what I'm doing here is getting the distance from the neutral axis to the center squared. Another very good question. I will answer to you in just after this slide. I will tell you what is the right answer to this. But before we go there, let me complete this calculation and represent to you what is the finding when we use 4 segments. Note when we used 4 segments, I've got the answer to be 160 inches to the power 4. So the question goes now, okay, the more segments I divide this shape into, the more accurate my result is going to be. If I use no segment, if I use the exact rectangle, I'll be getting 0. If I used 4 segments, I'll be getting 128. If I used 4 segments, I will be getting 160. So now it's converging toward a number. So now the question goes like, what if I used calculus? Divide by infinity, meaning you will be using integration. Because if you don't want to be doing those division divided into like smaller pieces, the next best thing is for you to use calculus and you use integration, right? So this is going to be the integration portion, which you will not be responsible for in the class, but it will give you a quick transition between the numerical way of doing things, which is giving you an approximate results, and the calculus way and the integral way doing things that it will give you the accurate results. Instead of approximate, you're going to get an accurate just by using a calculus. So basically the same thing, instead of me dividing it into a smaller 4 segment or 8 segment or 16, this expression in here, I'm going to write it in an integral formation. So the summation, it became an integral bracket, my calculus integration bracket. The y square has the y square onto it. Delta A became dA. Now, we know what is dA, delta A. Delta A simply is going to be this shaded area that we see in here. Simply is going to be the dy, which is the small and tiny strip in depth, multiplied by b. So this is b multiplied by dy, right? So basically what I will be doing, instead of me having delta A, I'll be replacing that with b dy. So this terminology in here will become y squared multiplied by b multiplied by dy. So now my variable, which is the y squared, and my derivative, which is dy, both of them have the same variable, which is y. Now I can begin my integration. My constant b, I shifted it to the outside of the integral bracket. And when I do my integration, I put it from the extremities of my shape, from this point all the way to this point. This point started from minus h divided by 2. That's why we have minus h divided by 2 to the top of my shape, which is this point in here, which is ended at plus h divided by 2. Now, if you know after that point, all what you will have to do is write this expression with the condition of the boundary conditions of your integral bracket, which is going to be 1 from, which is going to be from minus h over 2 to plus h over 2. Of course, b divided by 3, this is a constant. And all what I have to do, open a bigger bracket. Inside of it, I would have the top portion of my boundary, which is h squared divided by cube, minus the bottom portion of my boundary, which is minus h squared divided by to the power 3, which is cubed. And this is going to be a mathematical operation that can be easily solved using a fraction. So now, completing my integration, or rather completing my mathematical operation with the fractions, I will be getting the result as bh cubed divided by 12. Make sense? That's fine. You don't need to worry on it. But now, let me ask you something. If I were to, don't worry about the calculus part. If it did not, let's say, if you did not click on you, that's fine. I just kept it there to give you a quick refresher. If you started calculus and you, let's say, scarred you for life, I hope this slide made it a little bit more bearable for you to give calculus another chance in the future, maybe. But what we are interested in is this expression right here. So this expression in here, what it would give you is the exact solution for the moment of inertia for a rectangular shape, or in fact, any rectilinear shape. It can be rectangular or square. So if I were to have this shape of being 8 inches deep by 4 inches wide, I wanted to use a calculator and find me what is the moment of inertia based in this exact solution, bh cubed divided by 12. And I want you to compare it. Is it more than 128 when we divided the rectangle by 2 square? Or is it more than even 160 when we divide it by 4? The answer, you've got 170.667. I'm going to try to write it here. So give me 170.67. Of course, the unit always is going to be inch cubed. Sorry, inch to the 4, not cubed. Inch to the 4. So now, with that being said, note how when we use 2 squares, we've got 128. When we used 4 squares, we got 160, which is a little bit closer to the exact solution. If you were to be using 8 squares, you may be getting 168. If you're using 12 squares, you'll be getting 169.5. If you're using, let's say, 24 squares, maybe you're getting 170.1. So the more squares or the more division, more segments you use, the closer you are going to get to the exact solution. Does this make sense? Perfect. So now, moving on from this point onward, we are not going to take a rectangular and divide it by 8 segments or 12 segments. We know better than doing that. When I get a rectangle, I am going to use the equation I equal to bh cubed over 12. You just have to use it for a rectangular or square shape only. So now, this is the other geometrical property that we are introducing to you. When I showed you a square or rectangle last class, I asked what are the geometric property you can see. You told me I can get the area, I can get the parameter, I can get the depth, I can get the width of that shape. Now you can get the moment of inertia based on this equation. Make sense? Oh, good question, Spencer. We don't need to use it for rectangular shapes anymore. Absolutely not. What if I give you a circular, which I'm not, but if I were to give you a circular shape, this equation will no longer apply because this is specifically for rectilinear shapes, rectangles and squares. What if I give you a triangle? This equation will not work. What if I give you a T shape, a T section, or an L shape, a composite L section like we did last class? This equation will not work anymore. This is only for a rectangular shape. Make sense? So now I've got a question for you. If I got the same shape in here, but I've got it like this. This would be my 8. This would be the 4 inches. Basically, I'm orienting it 90 degrees to the vertical shape. I'm laying it flat, horizontal. Which shapes will generate the bigger moment of inertia. The vertical one, not the horizontal one, right? Yes, the first one or the tall one or the one on the right. Yes, absolutely correct. Absolutely correct. Now, can you look at the equation and justify your decision based on what the equation, how the equation is being expressed right now? Indeed, the height. The height is multiplied, is to the power of 3, right? So in the horizontal orientation, you've got 4 to the power of 3. Hence, in the vertical orientation, you've got 8 to the power of 3. So you can really get an exponential increase just from the height alone. Not even exponential. It's basically exponentials to the power squared. This is more than exponential. Make sense? So now, what did we say earlier? I'm going to go back. I'm going to go back to this slide in here. Let me clear it up. We said moment of inertia is a mathematical property of the area that describes the second moment of area about an axis. And this axis is the neutral axis. And what we said, it describes the object resistance to bending and to deflection due to angular rotation, right? So if I were to give you again the same objects that we were comparing, the rectangular one, 8, 4, and the one on the flat, 8 and 4. Which one would have a bigger eye? Quickly you said this would have a bigger I value than the one on the left. Now, I ask you another question, the same question in a different way. Which one more better suited to resist bending and deflection? I'm going to ask the question again. What we said in here, we said that the moment of inertia, it describes the object resistance to bending and to deflection due to angular rotation. So that's what the moment of inertia describes. And what this says, the more moment, if the object has more value in the moment of inertia, it can resist more bending. It can resist more deflection. That's why the one on the right, since you've got the 8 to the power cubed in our moment of inertia equation, it will generate much, much higher moment of inertia than the one on the left. And if an object just have a huge number of moment of inertia, right away you would select that for your beam situation, for it to resist the deflection in a beam bending effect, or for it to deflect flexure bending in a beam bending effect situation. Make sense? So not so scary now after all, is it? An equation, bh cubed over 12, you add it to your formula sheet and you go on. Most of the shapes are going to be, most of the shapes that you will be dealing with are going to be composite shapes of triangles. So this is basically what I'm trying to say, what I said earlier. If you've got a joist oriented on the vertical, as you see in here, or being oriented on the flat, as you would see in here. Why would you expect a joist on edge, sitting on the edge, is much stiffer than the joist laid flat, as you see in here, laid flat. Both of the objects have the exact same cross-sectional area, and the same material are still used. Because the orientation, the moment of inertia gets much larger on the orientation on being on the edge over than being on the flat. That's why. Absolutely right. Bigger moment of inertia, more resistance. So now, what we are going to do, we are going to present you with certain, instead of me going through the integral process for every single shape we are going to encounter, right? I'm going to give you those two slides, and those two slides would give you a pre-made exact formula for moment of inertia for common shapes. And our common shapes are going to be the triangle, the rectangle, the solid circle, and the tube. I'm not going to spend so much time on that. They are presented on the slide. You can even, at a later date, you can print them, reproduce that on your paper. Just an equations we are going to use from this point onward. Now, moment of inertia of a rectangle is most useful for wood design and deflection, because basically, if I were to look at 2 by 10 and a 2 by 10, it has the exact dimension of 38 millimeter by 235 millimeter. Yes, the last one is a ring. Oh, it's known as a tube, not ring. It's a tube. It's basically a hollow circle. So basically, if I were to calculate that on edge, the moment of inertia as it's sitting on edge, I'll be getting the value of 41.1 times 10 to the 6. If I were to calculate that on the flat, the answer is going to be 1.07. So on edge is 41 times stronger. Meaning, if I were to want to have one joist on edge to match its resistance to and of being on the flat, I need to get 41 pieces on the flat to match the resistance of one object on edge. So the moment of inertia is used to measure the stiffness of a structural member. Moment of inertia is assessed by the distance of the cross-section's material from the neutral axis. Now the cross-section with higher I value, higher moment of inertia, it has its material further away from the neutral axis. Makes sense, because the equation says what? The equation says h, sorry, not this equation, the equation, the general format of the equation is equal to summation of y squared multiplied by delta A. And the y squared is essentially the distance from the neutral axis to the center of this segment. And if that segment is furthest away from the neutral axis, you'll be getting the bigger distance squared. Now, in those two shapes, the following cross sections have the same area, but section 1 will have much higher moment of inertia than section 2. Why is that? You got it. You both got it right, because it's the majority of the mass is further away from the neutral axis. So basically, if I were to show you where is the centroid of those two objects, the section one, the centroid of the trapezoid at the top is further away, and so does the distance of the centroid of the trapezoid at the bottom is further away from the neutral axis. Section number two, the centroid is closer to the neutral axis. So it makes sense. That's why in steel section, we tend to use an I-beam, a beam that is oriented like such. You would have the center of that mass further away from the neutral axis, so we can get the most efficient beam. The same beam, if I were to use the exact same area, same dimensions, if I were to have it in double T sections like that, like almost a plus sign section, it's terrible for deflection and it's terrible for resisting bending moment. Do you follow the transitions of how things being made right now? Everything makes sense? Perfect. As long as it makes sense in the lecture room, in the lab, just matter of like understanding the technical calculation. So that's great. That's very good. Now, the moment of inertia, there is another equation that we will introduce to you. Is called the parallel axis theorem. The equations looks like this. A modification to the original general format of the equation. This is the original one for a single shape, rectangular, square, what have you. But this shape in here, the other one for the parallel axis theorem, is a modification to it. And if you were to logic yourself your way around it, simply all what it says is you take the moment of inertia of that individual segment and you add to it the area of that segment and the distance furthest away, or the distance from the neutral axis squared to the center of that segment. That's what this equation reads. And this is for the x, the same equation we'll have it for the y. And when do we use these equations? We use these equations whenever we are dealing with composite shapes. So moment of inertia I of a composite member is equal to I of the individual piece plus the area of each piece times the distance squared from the neutral axis. We will work this example in a class. For instance, if I were to give you a T shape like that, and if we were to assume this T shape is fully connected, meaning the top piece is connected to the bottom piece, we ask you to use the moment of inertia or calculate the moment of inertia, you have got to be using this formulation. So now, assume all of the shapes that I am going to show you right now are fully connected, except for the one in the middle. So if I have to ask you this one in here, and I ask you what is the moment of inertia about the neutral axis shown in here, simply what you will say, you will take the moment of inertia of one piece multiplied by 2. What about if it was on the flat? Simply we'll say I will take the moment of inertia of one shape multiplied by 2. If it was on the flat but not connected, of course, that's the key word. If it was on the flat but fully connected, you will have to use this equation in there. Now, what do you mean by fully connected? I want you to imagine this. If I were to have this cross section in here, and I'm building a beam, so my beam looks like this, and I've got a support in here, another support in here, applying certain loads, what have you. This beam would want to deflect. Will it want to deflect as such? Like that? Or will it deflect as each piece deflecting in its own accord, just sliding against one another, like this? If it's connected, it will deflect like this. If it's not connected, meaning those surface, the joint between them, they are not glued or screwed or connected to one another, each piece will deflect in its own. The object, the whole object will not deflect as if the depth is the deeper dimension. It will not behave as a deeper dimension, one segment with deeper depth. It will behave as two smaller pieces with a smaller depth, deflecting on its own, just sliding against one another at the surface, at the flat surface. I see. Because now what's happening is, Takashi, that's a very good observation, because what's happening for this shape 1, it's on edge. So basically the loads applied at the top, there is no connection happening on the horizontal, and the depth is not going to increase whether you connected them horizontally on the vertical or you did not connect them on the vertical. Let me clear this up. So now in this shape in here, let's say I decided to connect the vertical seam between shape number 1. The depth did not increase. Let's say I did not connect them. I left them like just slide, like adjacent to one another with no glue, no nail, nothing. As it deflects on the vertical, the depth did not increase. But if I were to connect two members on the flat, my total depth is this. If I did not connect them, I've got two members with a smaller depth. And the difference between here would be bigger D squared or smaller D squared added to one another. So for this shit in here, we are going to solve it out during the lab. I is required for the deflection calculation. Deflection is inversely proportional to the moment of inertia. Inversely proportions meaning if the one got bigger, the other will get smaller. If the moment of inertia got bigger, the deflection will reduce. As you can see in here, this is my deflection in the numerator side of the left-hand side. The equations on the right-hand side has got the I, the moment of inertia, at the denominator side, meaning it's inversely proportional. This is a deflection equation for a uniformly loaded beam. I will introduce that to you in the second half of today of this course material. Don't worry about this equation. It's only as a reference at this point. I will introduce it at the second half. But what's important to take home is the bigger moment of inertia, smaller deflection, which is good. Section modulus is the last sectional property that we are going to introduce, and it's related to the beam stresses at the extreme fiber. And the equation on that will be deduced from the bending stress equation, and we'll be introducing the bending stresses next week or the week after maybe. And simply, to make it simply put, the section modulus, simply the I, which is my moment of inertia that I previously calculated, divided by the distance from the neutral axis to the extreme fiber, the top or the bottom. So now for a rectangular shape, the section modulus is going to be the moment of inertia divided by the distance from the neutral axis divided to the top or the bottom. We have to the top or to the bottom. Since both of them is exactly the same, is going to be h over 2. So now the equation section modulus for a rectangular shape is going to be bh squared divided by 6. Hence, if you were to take the moment of inertia, you divide it by h over 2, you will be getting none other than bh squared divided by 6. It got a little bit overwhelming, I believe, in this slide, I think. Everything up to the moment, I think it was good. Now, once you introduce the section modulus, time is running out. I will be walking over the section modulus one more time through the lab material, and it would smooth and ease things out. Those are the same lectures notes from last week. I did not get the chance to finish them. I only stopped at the centroid equations, and I just take the same slides, moving on, finishing them today. So that's again the section modulus on the flat is this value in here. On the vertical is this value in here. And now this is bring this to the end of my class, my slides. I'm just giving you the last two slides being a summary of variables and equations. That's it.